Our closest galactic neighbor, Andromeda, sits roughly 2.5 million light-years away from Earth. If we boarded a standard spacecraft traveling at 28,000 kilometers an hour, reaching it would take 94.5 billion years. Even at the absolute speed limit of the universe, the speed of light, the journey would still consume 2.5 million years. Interstellar exploration is effectively impossible within a single human lifetime. To find a way out, we have to look to the mathematical source code of reality itself. In November 1915, Albert Einstein published a set of formulas known as his field equations. These equations describe how matter and energy physically warp the fabric of spacetime. Imagine a stretched mesh. When you place a heavy object on it, the grid curves under the weight. Gravity is the result of that curvature. These equations are nonlinear and incredibly complex, which means they behave like a high-level algebra problem. You can plug in variables and generate multiple, completely valid mathematical answers to the same physical challenge. In 1916, Carl Schwarzschild calculated the first major solution to these equations. He described a point where mass becomes so dense that spacetime wraps tightly around it, pinching the region off from the rest of the universe. This was the mathematical birth of the black hole. For over a century, these were treated as a theoretical curiosity. That changed in 2019, when astronomers captured the first actual photograph of a black hole. The math had been right all along. Curious, if the equations successfully predicted black holes a century before we saw one, we have to look at the other solutions they offer, and whether they provide a way to escape our galactic prison. In 1935, Einstein and Nathan Rosen calculated a second valid solution. They discovered the Einstein-Rosen Bridge, known more commonly as a wormhole. Think of the universe as a flat sheet of paper with 2 points on opposite ends. A straight line is the fastest way across, but if you bend the paper through the space above it until those points touch, you can punch a hole straight through. A wormhole applies this logic to our reality. By folding three-dimensional space through a fourth dimension, it creates a shortcut that could theoretically bridge millions of light-years in an instant. While the math supports this, the physics creates a significant hurdle. To puncture the fabric of space-time and hold a tunnel open, you need a concentration of gravitational force that defies conventional engineering. Currently, the only phenomenon known to possess enough gravitational power to rip open such a tunnel is a black hole. But black holes have a fatal flaw: their event horizon. Gravity there is so intense that nothing can ever escape. If you use a black hole to open a wormhole, you are trapped inside the tunnel forever. For a wormhole to be survivable, it requires an exit door, a mechanism with the power of a black hole that pushes matter out instead of pulling it in. The field equations provide a third solution to solve this. Coined in 1964, it is called the white hole. A white hole is the physical opposite of a black hole. Its event horizon forbids entry. Instead, it violently ejects matter into the universe. This completes the tunnel. You sink into the gravity well of a black hole, travel through the bottleneck, and the white hole spits you out on the other side. It is an elegant mathematical solution, but it creates intense debate among physicists. The question is whether white holes can actually exist in our physical reality. Critics argue they violate the second law of thermodynamics because they appear to reverse entropy. This would be like watching a shredded piece of paper spontaneously reassemble itself into a perfect sheet. However, quantum theory's no-hiding theorem states that information cannot be lost. This suggests that when a black hole eventually dies, it must eventually expel the matter it consumed, likely through a white hole. While unexplained events like the 2006 gamma-ray burst tease the possibility of these objects, the lack of definitive proof leaves this cosmic shortcut in the realm of theory. While we haven't found these tunnels in the cosmos, researchers are already testing whether we can force reality to follow this math in the lab. In 2015, a team of scientists successfully engineered a functional magnetic wormhole. By using superconductors to separate a magnet's poles across an invisible gap, they caused a magnetic field to enter one point, disappear, and instantly emerge from another. They proved that the topological logic of a wormhole could be applied to magnetic fields, even if we can't yet apply it to gravity. Einstein's equations contain other solutions that could bypass the speed of light, such as the Alcubierre drive. This concept involves a ship that doesn't move through space, but rather moves space itself. contracting the universe in front while expanding it behind. For over 100 years, black holes existed only as numbers on paper. The doors to the rest of the universe are already written into our mathematics. Whether those shortcuts can be reconciled with our laws of physics remains one of the greatest questions in science.